Hello everyone, welcome to Dakshana e-classroom program. So today we are going to start a new chapter and that's about electromagnetic wave. So let me just go back and tell you something about because this is how also this chapter is also somehow related to charge. So you must have studied about charge like electrostatic, then capacitor, is it, and electromagnetism and magnetism. So those were all things related to charge. In when charge, we try to understand basically charge. When charge is at rest, then we study and we define that subject as, we call it electrostatics. So when it started moving, then it generated current and we studied current electricity. So moving charge also produces magnetic field, and we studied that in magnetism. What was that? And then next things like changing magnetic field and flux and the EMI. So in all these things we derived a lot of things, actually a lot of result, like in electrostatics Gauss law, is it? Similarly Ampere's law in magnetism, and Faraday's law, right? So those laws were all discussed and studied, all that. And there comes one more thing, what will happen if a charge is accelerating, right? So that result, charge is at rest, then it is producing electric field and it's called electrostatics. When charge is moving, basically, then it produces current. We study that in current electricity, and it also produces magnetic field. So a moving charge produces magnetic field, understanding? But a accelerating charge actually produces both changing magnetic field and changing electric field, because in EMI what we studied is that, see, electric field, magnetic field, they are there, but are they related to each other? We were not knowing it earlier. But in magnetism we saw that, in EMI we saw that a changing magnetic field basically also produces electric field, right? So next thing comes is that, is it possible that a changing electric field also produces can also produce magnetic field? That was also one more question. So what happened actually, a lot of things were already discovered, and then Maxwell, what he did actually, he collected all the relations for cumulatively electromagnetism, starting from electrostatic and up to magnetism and EMI. When he studied all those relations actually, and those relations cumulatively we called Maxwell's equation. And I will write all those equations, Maxwell's equation of EM wave actually. And then based on that, in 1865, Maxwell predicted the existence of electromagnetic wave. At that time, electromagnetic waves were not known, it was not discovered yet, their properties, nothing was there. So he just theoretically predicted actually existence of electromagnetic wave. What he did actually, in electrostatic and magnetism, all that we understood that changing magnetic field produces electric field, understanding? And later on we studied also, I will tell you, that changing magnetic field also produces electric field, is it? So what happened, and Maxwell also by studying all those equations, he predicted the existence of electromagnetic wave, that accelerating charge particle produces electric field, changing electric field produces magnetic field, and magnetic field changing produces electric field. So in this way, an electromagnetic field means oscillating electric and magnetic fields are produced, and they propagate through the medium or even through the vacuum by itself. Nothing is additionally is required. So that was basically electromagnetic wave. So electromagnetic wave source, we can say it's simply an oscillating or accelerating charge particle produces electromagnetic wave. Later on in 1885 something, Hertz did one experiment, and he even experimentally demonstrated the existence of EM waves or electromagnetic waves. Later on, Marconi and J.C. Bose also generated EM waves in the laboratory of smaller wavelength. Before that, Marconi, Hertz developed electromagnetic wave of very large wavelength, that's around 6 meter wavelength. J.C. Bose developed small wavelength wave, electromagnetic wave, that is from around 6 mm to 25 mm or 5 to 25 mm wavelength EM waves were developed by J.C. Bose. Later on, actually, Marconi Marconi was successful even like producing very small wavelength EM wave, and those were propagating even for like longer time, or sorry, longer distance. And that's how actually Marconi even discovered, or for the first time he actually established wireless communications, and he also discovered radio. So Marconi, so that was how like things developed actually with the time. So let's start from the basic, like where Maxwell studied all the four equations or five equations considering the Lorentz force. So let me first write what were those Maxwell's equations. So Maxwell's equation here, these are actually like equations from electrostatic and magnetism, is it? So first, and the cumulatively we call them Maxwell's equation. So Gauss law of electrostatic, what is that? It's in closed integral over closed surface E dot ds is equal to q enclosed divided by epsilon naught. And you must be even clear with this, what this relation, what this expression here, E dot ds basically your electric flux, and with this relation we can calculate the electric field due to a charge system, where q enclosed is, we consider one Gaussian surface, and whatever the charge is coming inside that, that should be placed only, the outside charge is not considered in this q enclosed, and divided by epsilon naught. So by simplifying this we get electric field. And this actually, the Gauss law of electrostatic also prove the existence of this, also prove the existence of charge, is it? Or separately, basically like positive and negative, positive and negative means like separately there, because in case of magnetism, is it? So if we write this Gauss law of magnetism, what is that? And that is integral b dot ds, this is equal to 0 actually. For magnetism it comes 0. Why it is 0? Because here if I write M enclosed, or magnetic monopole strength enclosed multiplied by mu naught, then what happened actually here, there is no monopoles exist. So this also proved that monopoles in magnetism or magnet does not exist. Right? Similarly, there was another, that is Faraday's law, and this is a changing magnetic flux produces EMF, and that can be related to electric field. So this is E dot dl is equal to minus of d phi b by dt, where d phi b by dt is the changing magnetic flux. So here a changing magnetic flux produces EMF, and we can understand from here that changing magnetic field, magnetic flux can be changed. One of the possibility, it can be changed by changing area, it can be changed by changing the angle between magnetic field and area vector, and another comes is by changing the magnetic field also we can produce actually magnetic flux or changing magnetic flux, and that case it produces actually electric field. So it proved that changing magnetic field can produce electric field, right? And the last one, the fourth one, is Ampere's law. Ampere's law is integral b dot dl over closed loop is equal to mu naught into I enclosed. So, and before I will come to this point back, and the fifth one is Lorentz force. Lorentz force, basically it gives you the force on a charged particle in electromagnetic field, and that force on a charged particle is given by Q times, this is E bar plus V bar cross B bar. This is the force on a charged particle. This is a force on a charged particle in electromagnetic field. Right. So what actually, like, Maxwell studied like cumulatively or collectively studied all these relations, and based on that he predicted theoretically the existence of electromagnetic wave. So Maxwell predicted theoretically the existence of EM wave. That was in 1865 year, right? And he actually, when he was studying, he finds something contradicting here. So let me tell, because that contradiction basically generate the need of displacement current, and that is an important topic for this chapter. So let me first tell you why, like what is something contradicting about this Ampere law, then we will talk about displacement current. Okay, so let's see something about Ampere's law first thing. So here we are considering one capacitor connected to one battery via switch. Okay, so let's say at t is equal to 0, switch is on. Right, switch, we are keeping it on. What will happen? Current will flow in this, and here we will see. And what Maxwell did, actually he did some compass, something like here, and some deflection was observed, and he placed one compass here also, and there also deflection was observed. So let's say this is place 1 and 2. So Maxwell observed deflection in magnetic compass at both points 1 and 2. So that what it mean actually? This means there is magnetic field at point 1 and there is also magnetic field at point 2, correct? Because so now you can see, if I'm considering, like let's apply Ampere's law by considering one Ampere loop at point 1 and at point 2, then we will see something. So this was just observation that like Maxwell observed actually experimentally, that there is something deflection coming here, and this deflection is proving that there is a magnetic field actually. So this prove actually that there is magnetic field at point 1 and 2. So he tried to relate that magnetic field with the Ampere's law. So for this location, he consider this Ampere loop. Let's say this is a loop of, let's say, radius r, and then what for loop 1. Okay, so let me write, this is a loop 1. For loop 1, what we can write, integral b dot dl is equal to mu naught into, so when switch is on, what will happen? Some current will be there. Yes, definitely we will see, because capacitor will be charging, so some charge will be like appearing, and during that process there will be current flowing through this wire, and we will see. So mu naught into I enclosed, and yes, this implies some B will be there, non-zero, and that's why there is a deflection. Clear? Now let's consider next case. Same situation. So one way is I can consider it in this manner. Let's consider one loop here. So do you see any current, like when switch is closed here, then there is current here. But is there any current we are seeing here? Is it? So this is loop 2. Clear? So now for this situation, for loop 2, now if I apply integral b dot dl, that means mu naught into I enclosed must be 0. So this implies here b must be 0, but it was not. So this is the contradiction actually, that according to Ampere's law, the magnetic field at this point must be 0 because there is no current enclosed in this loop, because this is in air, there is no conductor passing through this loop. So that's why, and we can actually see this same situation by considering a different system, just setup where I'm choosing the Ampere's loop in different manner only. So sometime this is, and we choose Ampere's law Ampere's loop like this. So it's sort of like pot shape surface, where you can see here there is only current entering but there is no exit current. So overall you can see no current through this boundary of this surface, there is no current crossing actually, right? So this is a pot shape surface, and we know actually no current is crossing this spot, so that's why there also integral b dot dl should be equal to what? 0. And this implies b equal to 0, but b is non-zero. This is true. It should be, but it is actually this. So there arises problem that we are observing experimentally some magnetic field in this region, but by Ampere's law we are getting the magnetic field should be 0 in this region. So then Maxwell thought about it, and he thought that something is missing actually here, and that's why we are getting the contradicting results. So Maxwell then studied and discovered that, and that was basically the concept of displacement current, and with the help of that Maxwell modified this Ampere law, and we study that Maxwell Ampere's law. And let's see, so first let me define what is displacement current, and with that this contradiction will be resolved. Okay, so first let's see what is displacement current. Okay, so next is displacement current. See it here actually. So now what is happening, this is a capacitor plate and connected to battery switch, and it's let's say on at t is equal to 0, battery and capacitor plates. So what will happen, initially the capacitor was uncharged, then what will happen, it will start charging, and let's say let at time t charge on capacitor plate is Q. Okay, and it will be because it's charging, so Q will be changing, right? And I can write electric field, is it? Electric field in between the capacitor plate. So what I can write, E is equal to Q divided by A multiplied by epsilon naught, where A is the area of capacitor plates. Right? This is the electric field in this region. We can see electric field will be directed in this manner. E. What is the electric flux? That means phi E will be equal to what? This is E into A, and that comes out to be Q divided by epsilon. Right? And now you must be agree here that when switch is on, because initially the capacitor was uncharged, so it will be slowly charging. Slowly means like here I know that it's not proper term. Basically, it doesn't take much time to charge the capacitor completely. But just let's assume that we have slowed down the process. Okay, so we are studying it in that way to just understand this concept. So let's say like this charge on this capacitor plate is increasing. Then what will happen? Definitely charge is increasing, electric field in this region will be increasing, and flux, electric flux in this region will be also changing, right? Because electric field in the region is changing. So now what will happen? If I differentiate with respect to time, then what you will get? This is d phi e by dt equal to 1 by epsilon naught times dq by dt. And what is dq by dt? That's current, right? So this implies is dq by dt equal to epsilon naught times d phi e by dt, and this term is called id, and this is called displacement current. So up to now we studied simply current, right? But actually that current that we have studied, or you have studied up to now before this concept, that was simply termed as conduction current. So conduction current arises because of flow of charge through a wire. Electron move, charge flow, then current arises, we call that conduction current. In this situation, definitely you can see here there is no charge crossing from this plate to that plate, but still there is some current in this space, is it? And that is because of changing electric flux or electric field. So this current is defined as displacement current. So current which arises because of changing electric field or electric flux is termed as displacement current. So the current due to changing electric field or electric flux is called as displacement current. So Maxwell now found that actually there is also current in this region, and that current is not conduction current. This current is displacement current. So whatever the magnetic field we were observing, or Maxwell observed in this region, was contribution of this current, displacement current, but that was not due to conduction current, because conduction current in this region is 0. So this term is like quite important. Many times in exam or in problems you are asked about displacement current, what is that exactly, how it produces, maybe sometimes relations. So ID, we denoted ID means displacement current, D subscript. So this is equal to epsilon naught times d phi e by dt, and you must be clear how we got it actually. And we got simply this is called displacement current. So it's denoted by ID, and this is equal to d epsilon naught times d phi e by dt. And IC, that is called dq by dt, we call this is conduction current. So the current due to flow of charge, or specifically electron, I can say, is called as conduction current. Then after this displacement current concept, Maxwell modified that Ampere's law, and it was like Ampere-Maxwell law, or we can call it Maxwell-Ampere's law. And then that fourth result, Ampere-Maxwell law, was predicting everything correctly. So this is how we needed the concept of displacement current. And then after this, the modified Ampere-Maxwell law is So it's basically modified Ampere's Maxwell law, and now I can write integral over any closed surface B dot dl is equal to mu naught into I conduction plus I displacement, and this can be expressed as mu naught into I conduction plus mu naught into epsilon naught into d phi e by dt, and now this is modified Ampere's Maxwell law. This gives you the result for existence of magnetic field in every region. So normally, like what happen actually, IC conduction current and this I is displacement current. In general terms, whatever the cases, like when some conductors are involved basically, or wire through which electrons are moving, so normally conduction current is available like most of the time, but displacement current is also there. So whenever there is some space, vacuum is there, no conductor is there, then definitely there will be some displacement current. And because another thing is that whenever there is changing electric field is involved, definitely there will be displacement current also. So actually, like as there is rare possibility or very less possibility of constant electric field, or it would be better actually, I will write that whenever there is electric field, changing electric field is involved, at that time displacement current will be there. And if there is one conductor and where electric field is changing or maybe the current is changing, then what will happen? There will be possibility of existence of both displacement and conduction current. So means in one reason there may be only conduction current, may only displacement current possibility is there, or both current might be present simultaneously. So depending on whatever it is present, we need to just consider that part, and cumulatively if we are considering all this effect, then there will be no problem in Ampere's law, and we just call this as modified or Ampere's Maxwell law. So I hope like by this time you must be clear with the concept of displacement current. Okay, let's see one application based on displacement current. So here a problem is given: a parallel plate capacitor with circular plates of radius 1 meter. Capacitance is given as 1 nanofarad. T is equal to 0. It is connected to a battery and switch is closed actually at T is equal to 0. So means before that there is no charge on the capacitor. Resistor is connected 1 mega ohm and so on. And it's also given to you that charge on the capacitor as function of time is also given to you. So first, like let's see, Q is equal to CV 1 minus e to the power T by RC. But we must C is equal to what? 1 into 10 to the power minus 9 C capacitor into V is 2 volt. So Q is coming out to be 2 into 10 to the power minus 9 coulomb. And RC, when we write tau equal to RC, R is 1 into 10 to the power minus plus 6 multiplied by C is 1 into 10 to the power minus 9. So tau is coming out to be 10 to the power minus 3 per second. Okay, then I can write Q as function of this is Q naught. Then we write it Q naught. This is 1 minus e to the power T by 10 to the power minus 3. So we got charge. Now here it is asking like magnetic field at point P. So we will consider one Ampere loop here. This is Ampere loop. right? Because total radius, these are circular plates, and total radius is given as 1 meter. So means it is exactly midway. So this radius will be equal to what? It's simply half meter. So now we can go through like because for this Ampere loop we will apply integral B dot dl is equal to mu naught into I conduction plus I displacement. So there will be no conduction current in this region. There will be only displacement current. So B, another point is it's symmetrical. So we can say like actually at this loop or along this loop B will be constant, and dl we know easily it will be along same. Alright, so we know mu naught. Now we need to calculate actually ID, displacement current. So what is ID? ID, we just told this is epsilon naught times d phi e divided by dt. So for phi e we need electric field. So electric field in between the, like if charge is q, is it, on the plates, then electric field can be written as what? E is equal to q by a epsilon naught, and area is what? Area of this plate is pi into radius, total 1 meter. So E is coming out to be q divided by pi into epsilon naught into 1 square. So this is q by pi epsilon naught is the electric field. Then flux, electric flux through this loop, phi E through loop, that will be equal to what? Phi E is equal to E multiplied by its area of loop, and that is equal to q by pi epsilon naught multiplied by pi into radius is 1 by 2 half, basically half square. So this comes out to be q by 4 epsilon naught. Then displacement current is equal to what? It's like 1 by 4 epsilon naught into dq by dt, and we already have expression for q, so that I can differentiate it, then I will get the value of id. So simply this is coming out to be id, just 1 second, we simply got phi e, and id is equal to epsilon naught times, so just a small mistake here, we got phi e is this, and id I will write id is equal to epsilon naught times d phi e by dt. This is epsilon naught times d phi, means differentiation of this 1 by 4 epsilon naught into dq by dt. This cancel out and it's 1 by 4 into dq by dt. So dq by dt I can calculate from here. So let me just do it here. So dq by dt is coming out to be Cv, differentiation of 1 will be 0, and we have the value of q naught basically also. So it's q naught multiplied by minus x plus e is power minus d by rc divided by rc, that is equal to tau. So this is dq by dt. Then displacement current is equal to, this is a dq by dt, I am substituting it. So q naught is how much? This 2 into 10 to the power minus 9 divided by id, this is 1 by 4, that is equal to, okay, 1 by 4 is that, and dq by dt q naught by tau, tau is equal to 10 to the power minus 3 multiplied by e raised to power t divided by 10 to the power minus 3. So this is displacement current. Next thing is I need to erase some part. Okay, now we need to substitute things here actually. So then I will get b dot dl is 2 pi into r is 1 by 2, and this is equal to mu naught into id. id is this, so this is basically 1 by 2 into 10 raised to power minus 6 multiplied by e raised to power t. T it's also Benson, it's talking about the time actually. We are supposed to find the time. It's Benson actually, I missed it. And t is equal to 10 raised to power minus 3. It's second, it's asking the field, magnetic field between plates at this moment of time. So then I can substitute t 10 raised to power minus 3 divided by 10 raised to power minus 3, and here we are getting mu naught into 1 by 2 into 10 raised to power minus 6 multiplied by e power minus 1. Just substituting all these values, and b is equal to dividing 1 by 2 cancel this, so mu naught into 10 raised to power minus 6 into e to the power minus 1 divided by 2 pi, right? And then substituting all these values basically and simplifying it, we get the value of B is equal to 0.74 into 10 to the power minus 4 Tesla. That you can simplify substituting the values. So this is the method actually. Yes, it's like a little bit lengthy, but not complex, because this expression is, you must be already familiar with this, even it's provided to you. Now just value we calculate. So mainly this is the relation, and for calculating this I have calculated separately displacement current, and that is also easy. So this is how like you can solve problem based on displacement current. Okay, so we saw that actually Maxwell studied all the results derived for electromagnetism, means for electrostatics and magnetism, and based on that he theoretically predicted the existence of electromagnetic wave, but he never experimentally proved or demonstrated that. In 1885, Hertz was the first scientist who actually demonstrated or produced the EM wave in the laboratory. The setup was like that Hertz used looks like something this, and let's try to understand how exactly like from here we understood or like Hertz produced the electromagnetic wave and proved the existence of electromagnetic wave that Maxwell theoretically actually like explained. So here the setup, here we have one AC source which is providing voltage or like current, and here step up transformer which is actually like amplifying the voltage or magnifying it. So finally, and these two terminals are connected to conducting metallic sphere. So these are two metallic spheres. Now what is happening here actually? So when like high voltage is coming from here, these spheres are acting like capacitors. They are capacitor. So these metallic spheres are capacitor. What will happen? They will charge, and when they are charging, the potential difference between like this will be also potential increasing. So if it is positive, it will be negative. So the potential difference between these two will be like very high, and that potential is basically transferred here. So the potential difference between these two spheres will be same, because these are connected by a conducting wire and some small metallic balls you can consider, or like just metals. So now here what is happening, this gap is very low, is it? This separation D is very small, and when V is very high, right, then what we know, E is equal to V by D. V is high, D is small, then what happened? Electric field E become very strong. Definitely you must have heard some spark actually. So whenever like you are bringing two conducting like current carrying wires closer, then we saw some spark. So is it like why, what is that exactly? Have you ever thought about it actually? Spark, in case of spark actually what happened when we are bringing two conductors which are at some potential difference at very close, is it? Just consider this case, let's say V is equal to 100 volt and D is equal to 1 micrometer. Then what would be the magnitude of electric field? That you can consider, it's 100 divided by 1 into 10 to the power minus 6, and that will be like 100 into 10 to the power 6 voltmeter. And this electric field is very strong. The dielectric strength of air, is it, means the potential electric field up to which air can act like insulator, that is equal to 3 into 10 to the power 6 voltage meter. So means when we are applying a potential difference of 10 to the power 6 3 into 10 to the power 6 at a separation of 1 meter, air will still act like insulator. But when things goes beyond this or more than this, then air also ionize, because this much strong electric field pull the electron from the air molecules and current is conducted, and that current basically appear like a spark. So exactly same thing happen here also. So what is happening when potential drop across these two spheres is very high, that means the electric field between this gap is very high, and that result in ionizing the air molecules and it pull the electron from the air molecule. So what happens, some current actually flow and that appear like a spark. So when high potential, its spark is produced here. And what is a spark? So a spark means like some like electrons are pulled from the air molecules or from the molecules, then what will happen? An electric field is there, so they will accelerate. Understanding? So spark means basically here electrons are accelerated, is it? Are accelerated because of strong electric field. And Maxwell, that's what exactly like said, accelerating charged particles are source of EM wave. So these accelerated electrons means accelerating charged particle produces what? Like we know charged particle at rest, it produces electric field, is it? If it is accelerating charged particle means moving, then it will produce actually changing electric field, and that changing electric field we have seen it can produce magnetic field also, or I will say the changing electric field will produce changing magnetic field. And we have seen that a changing magnetic field can also produce changing electric field. So that is what exactly happened here. Accelerating charged particle produces changing electric field, that ultimately produces changing magnetic field produces electric field, and so on. This process keep on continuously going, and that's why like that's how here electromagnetic waves are produced. So here what is happening actually, now with this source we are continuously changing the polarity, is it positive negative, so electrons are like moving this way, like it's accelerating up down. And one more thing, the frequency of electromagnetic wave generated, is equal to the frequency of oscillating charged particle, because you can see the charge electron will be like one, it will moving this way because when polarity positive here, then positive negative, then electron will be accelerating upward, and after some time because this AC source it will be changing the polarity exactly at same frequency, this will be also changing. So what we can say, this polarity will change negative positive, then electron will accelerate down. So in this manner charged particle, in simple term, in general term, I can simply say that charged particles are accelerating, or accelerating charged particles will definitely produce changing electric field, and that ultimately produce changing magnetic field, and changing magnetic field back to electric field. So that way electromagnetic waves are generated, and that was like so now okay, here it is generated, then Hertz produced some setup like here, so connecting wire placed like this and two metals balls. He observed like one was like he observed some spark actually here, and he placed some like galvanometer, some deflection was also observed here. So this proved that actually something is being transferred from here to there, and how it is possible, like so that is only because of electromagnetic waves. So this was the first experiment of Hertz which proved the existence, or which basically produced electromagnetic waves in the laboratory. Later on J.C. Bose also produced electromagnetic wave in the laboratory. That wavelength was like quite small, so the wavelength of wave produced by Hertz was here wavelength of these wave was around 6 meter, and J.C. Bose also produced, and like that was from 5 mm to 25 mm wavelength electromagnetic wave. Later on Marconi even produced a smaller wavelength electromagnetic wave, and he even set up for the first time wireless communication system, or communicated wireless, and later on he also discovered the radio. So this was all about the production of EM wave. And so first few things here is that simply what is the source of EM wave? Source of EM wave is accelerating charged particle, or I will say oscillating charged particle. The frequency of EM waves generated is equal to the frequency of oscillating charged particle, and the energy that is ultimately being transferred in the form of electromagnetic wave is coming from the source that is like oscillating charged particle, which the source which is oscillating means like here you can say the energy is coming from here because this is supplying, and that is ultimately resulting in oscillating or accelerating charged particles. So these are few points, let me write them so it will be better. Okay, so these are the same thing actually in point about generating EM wave. So first thing is only accelerated charged particle can produce EM wave. A charged particle which is at rest or either moving with constant velocity, neither of them can create an electromagnetic wave. It must be accelerating, it must be oscillating also. Like, so acceleration is must, can be oscillating. So then only accelerating charged particle radiate energy in the form of electromagnetic wave. Oscillating charged particle produces oscillating electric field, like oscillating electric field, because we have seen it just now that changing electric field can produce magnetic field also, and changing magnetic field can produce electric field also, vice versa. So exactly same thing happen here actually. Oscillating or accelerating charged particle produces oscillating electric field, which produces oscillating magnetic field, and this magnetic field produces again oscillating electric field, and this way it keep on like electric to magnetic, magnetic to electric, and so on, and it keep on moving through the space. So oscillating electric and magnetic fields regenerate each other and propagate through space as wave, and we call this as electromagnetic wave. Electric charge oscillating with frequency f will produce EM wave of same frequency. So the frequency of wave will depends on the charge that is oscillating, the frequency of oscillating charge, and this is simple. The energy of electromagnetic comes from the source, that is means the energy which is energy of oscillating charge. So that is how this is a few point about production or generation of electromagnetic wave. Next comes like, okay, now we understood that is how Hertz for the first time he proved or like demonstrated the production of electromagnetic wave, and these are few points about it, but still it's not enough. There are many more things about electromagnetic wave, and let's see some properties of electromagnetic wave. Okay, so when we talk about electromagnetic wave, the oscillating electric and magnetic field, the relation between them is that their plane are always perpendicular. Means if oscillating electric field is in, let's say, xy plane, then magnetic field will be in xz plane. So here you can see this electric field is oscillating in xy plane and magnetic field is actually in xz plane, and electric field and magnetic field both are always perpendicular. And here if I say the wave is propagating in x direction, then these are what, like normal wave equations, is it? Oscillating electric field, magnetic field, and wave you must have studied. So exactly by using same general like standard notation, I can write here the equation for electric field and magnetic field. So E is equal to, let's say, E naught sine of omega t minus kx if it is propagating in x direction. Similarly, B can be written as, so it will be like electric field will be in you can write j cap, and B is equal to B naught sine of omega t minus kx, and this is k cap, right? The relation between electric and magnetic field we can also have. So here this E bar is equal to like C bar cross B bar, right? Or magnitude. C is what? Speed of light. So speed of electromagnetic wave, speed of electromagnetic wave or EM wave in vacuum is equal to 3 into 10 raised to power 8 meter per second. In some medium it will be different, and you can just consider, because light is an electromagnetic wave, so exactly the property of light is exactly property of EM wave, and properties of light we have studied a lot, so all those properties are applicable here also. Few things that is different here, I'm noting them, I'm writing them here actually. And another thing is the speed of light, C, is related in this manner. It's mu naught by epsilon naught, where mu naught is magnetic permeability of free space or vacuum. Similarly, epsilon naught is permittivity of vacuum. If EM wave travel in some medium, if EM wave travel in some medium says that mu is permeability of that medium, and epsilon is permittivity, then speed of electromagnetic wave in this particular medium V is related in this manner, epsilon into mu, right? And EM wave are transverse in nature, the relation between that is how, and always we can write the C bar, you can write C bar will be parallel to along E bar cross B bar, because you can see here actually like electric field, magnetic field and direction of propagation, all three will be always perpendicular. And here we can see if E is in, let's say, y direction, then I will curl my fingers in the direction of E cross B, so B is in Z direction, then thumb is giving you the direction of X, and that's what exactly the direction of propagation of electromagnetic waves. So we have this relation, and we can have like this relation also. So here you can see it will be like, we can check it actually, because this is the condition given. Then for this is the B, so B cross C should give you the E, so it will be basically here B bar cross C bar will be this relation B naught. And similarly you can write C bar cross E bar will be equal to B bar, because we can check it here. So C is in this direction, E is in Y direction, X, Y, and then Z we are getting exactly B naught direction. So this is the relation between electric field, magnetic field, magnitude, and C is the speed of light. Speed of electromagnetic wave in some medium is given by this expression. Speed of EM wave in vacuum, that is equal to C, and it is related to permittivity and permeability in this manner. And here this is the equation where omega, angular frequency, you must be knowing omega is equal to 2 pi f, where f is the frequency of the wave and omega is angular frequency. K is termed as wave number, that is related to 2 pi by lambda. And here this V is equal to, or C is equal to lambda into f. So this relation is normal that you have already studied. C is the speed of electromagnetic wave, you can write lambda is the wavelength, and f is the frequency of that electromagnetic wave. So here electromagnetic wave carry some energy, right? First thing is, these are few things like you must remember. This relation is straightforward, this used a lot sometime, like basically, so just remember this. In terms of magnitude you can write C equal to E cross B, simple terms, and magnitude wise like B naught is equal to E naught by C naught, so that you can use in terms of magnitude. And this is for direction actually, okay, like this is not exactly for magnitude, it's just for direction, so I should not write that exactly. Yes, I need to modify here. This is the relation between electric magnetic field and C, speed of light or speed of electromagnetic wave. This is also true, but it is only for basically direction, not for magnitude, so I should rewrite it. So this is parallel to B naught bar, and similarly you can write C bar is parallel to E bar cross B bar, not equal exactly, because magnitude it will be like different. So this and these are few things. Here you can see the that is how changing electric field will produce changing magnetic field, changing magnetic field will produce changing electric field, and that way like it travel. And electromagnetic wave does not require any medium for traveling, they can travel in free space also. Electromagnetic wave carry some energy, and that too they carry in terms of electric field and magnetic field. So energy density in electric field and magnetic field, what is that we have already studied. Let's now talk about the energy density that is carried by the electromagnetic wave. Okay, before talking about energy of EM wave, let's see some application, basic application of electromagnetic wave and its like equation something. So plane EM wave of frequency. So here you are given frequency 25 megahertz and travel in space in x direction. So it's basically c bar. I can write wave is traveling along x direction, and at a particular point in space and time, electric field magnitude is given as 6.3, its direction j cap voltmeter. What is b bar at that point? So means we need to calculate magnitude of b, magnetic field, and its direction also. So first thing is, here you can see it's traveling in I cap, electric field is in j cap ey. So then what is the relation? First let's say magnitude of b is equal to what? E by c. We have just seen the, so it's like 6.3 divided by c is 3 into 10 raised to power 8. So this comes out to be 2.1 into 10 raised to power minus 8. This is your Tesla. This is the magnitude of magnetic field. And what will be its direction? So we know, actually you can either remember the E bar cross B bar must be parallel to C bar, is it? So here you can write, you can consider E bar, it's J cap. So when it can come, J cross K only can give you I. So that this implies B bar must be along K cap. So then finally we are getting B bar is equal to 2.1 into 10 to the power minus 8 K cap Tesla. So that's straightforward, simple question. And similarly here, magnetic field in a plane EM wave is given by this. Write the expression. So first thing is, B is along what? It's along y direction, and wave traveling or propagating along x direction. How? That is from here, kx minus omega t or kx plus omega t. So it's traveling in basically negative x direction. That too, it's negative x direction. Okay, so now we can see it. Let's say this is a x, y, and z. So c bar is along this, c bar minus x, and b is along y. So b is along y direction. Now we need to check for E. Is it? So first is magnitude of E is related to what? Magnitude of mod E is equal to C into B, that is 3 into 10 raised to power 8 multiplied by 2 into 10 raised to power minus 7, and this will be like 60 voltmeter. So magnitude of electric field, we got this. Then I will write E is equal to magnitude 60 into sine of rest. Remaining things will remain exactly same. Omega kx, this is 10 raised to power 3 x plus omega, that is 1.5 into 10 raised to power 11 t. Now next point is, it will be in along which direction, is it? So we should know actually that this C bar is parallel to E bar cross B bar, is it? So E bar cross B bar means like E cross B. Here see, if E is along Z direction, then E cross B, then it can give you this direction, E cross B, x, y, z. So means it what? B must be along Z direction, and that too it's clear because here standard things are there. X is along like wave propagating, y magnetic field. So definitely it will be like third perpendicular direction is Z. Only the point is whether it's like positive Z or negative Z. That we can check by this way. So they like you can say Z, then E this is E cross B will give you negative this, and if it is E cross B, then it will give you positive x direction. So this is coming out to be Ez. So you can write it K cap also. This is the electric field or electric field wave. So that is given as. So this is about that problem. Let's continue from here onward.